All right. This check-in has got our person winning a stuffed animal in a carnival. They extended it 0.5 meters out. That's a distance. Really, it's a displacement, I guess. It's got a direction, 0.5 meters out. That's not a 5. 0.5 there. With a force of 30 newtons, that's the force. In a celebration of their victory over the Carnies. They made it really dramatic by taking 5 seconds. That's a time. 5. What was their power output? Power. Wow. I put the formulas on here. Wow. So power formula says work divided by time. Here we go. Power. Work divided by time. My W's don't look very good today. I'm sorry about that. I got time, 5 seconds. I don't have work. That's not a W, that's not a W, that's not a W. But it tells us that work is force times distance. So instead of work equal, or power equals work over time, I can say power equals force times distance over time if work is equal to force times distance. And I've got force and distance, so that'll be fine. I can do that. Let's see. Force is 30 newtons. Distance is 0.5 meters. And time is 5 seconds. Here we go. All right. 30 times 0.5 is 15, I think. That's half of 30. And 15 divided by 5 makes 3. What's the unit for power again? Anybody unit for power?
Watts.
What? Oh, watts. Yes, watts. Watts. There's some of these questions on the CTBA, which will be on Monday the 22nd. Our first Monday after we don't have a Monday. First Monday of our first 5-day week back from our group of 4-day weeks. So today we are doing the centripetal force stuff that we did in that lab yesterday. Yeah. So allow me to demonstrate here. Y'all know, what are those things called that spin things around to separate them out? You spin it around real fast, and then that's not meant to separate things, right? That when you spin it around so fast, the high mass things go out to the outside more, and the low mass things aren't pushed as hard to the outside, I guess, or something. You know what those things are called? I'm thinking of a centrifuge. What are you saying?
Centripetal force?
Yeah, I'm thinking of a centrifuge. A centrifuge is a real device that separates things out according to their mass, or at least it can. That's not what I would call this. Why is? Okay, I think I need to use the other side.
Like when you spin like a rope around, and it just stays making a circle. That is centripetal force.
Yes. Well, that's centripetal force. Centrifugal force is just what you feel when there's a centripetal force on you. Because, y'all been on those rides at the carnival? Jada, have you been on those rides at the carnival where you're like on the swings or something? And you just spin around like this?
Yes.
Yeah.
I've been
I don't
the
think they
Six Flags ride.
This one? Yeah, Six Flags. With the swings. Those swings are so high up. I don't really like it that much. It's a little scary.
I love it.
To
I
me.
take pictures while I'm up there.
No, I didn't like it. I freaked out. I didn't think I was going to freak out, but it was bad.
I like to go
It's boring. It's not even that fast up there.
Yeah, but it's so high up and it's like, ah! I didn't like it.
Yeah, not me. I just
I'm much
record
rather
it.
ride the
Take
type.
pictures of
Is this
lights.
better? Here, I'll be over here. Yeah, see? So what's happening here is it's spinning you around.
Giant is better than
No,
Giant.
no. Keep your mask on.
My bad, man.
Uh,
Yeah, it is.
All right, listen. I'm glad you like the roller
My bad.
coaster. So yes, what the swings are doing, moving you in a circle like this, they're really accelerating you in a straight line. They're accelerating. Dana, what are you doing? They're accelerating
What
you.
are you doing?
And I'm teaching you. Look, they're accelerating in this straight line here. The only reason you're staying in a circle is because of the chains on the swings are attached to your chair there, and they are pulling toward the inside of the circle. If they weren't there, nothing would be pulling, and you would go, woo! I got to demonstrate last class because this thing fell off, and, and I was trying to spin this thing, and it just, woo!
Woo!
I wonder if it'll do it again. I don't want to break my computer over there. I'm not gonna tempt fate here, but
The rope.
yeah, the rope. But yeah, here, you know what I can do? I can probably do this a little bit. So if this thing swings around, then whew. Let's see. I guess it's not going to come off. That's fine. It's probably for the best. But if this thing were to come off, if the rope were to break, which it did last class, and I really wished I had the video on, then this thing would travel, like if I was swinging it like this, and it was going slow motion,
Keep on spinning that way.
if the rope broke right here, at this instant it is moving zoom, like straight towards my face. So if the rope broke right there, then it would go boom and hit me in the face, right? It's not going to keep going in a curve. It would move in this blue looking line tangent to the circle. Y'all remember your geometry word? I believe a line tangent to the circle is one that intersects the circle at only one point, and a straight line, so it goes tangent to the circle. Like last class, when I had the stuffed animal in the check-in, so imagine that the check-in is a circle and the stuffed animal is a tangent. And I started saying that, oh, well, so, you know, we've got the power, calculating the power. There's a stuffed animal. Oh, my dog likes stuffed animals. And I was on the tangent to the circle line right there. But that's how you can remember. Okay. Yeah, so like, what else we got? You know the rides, these are real carnival rides where they spin around and you're inside like a disc and it pushes you. You feel like you're getting pushed against the wall.
And then you can go like upside down.
Yeah. What's really happening is the wall is pushing in to keep you moving in that circle. Like, if that ride were accelerating, like that ride is accelerating you, it's accelerating you in this straight line. What you feel is, since it's accelerating you so fast out, the wall has to push really hard to keep you in. But that is what the wall is doing. It's keeping you in. It's pushing toward the center of the circle. If that wall weren't there, you would fly out at a line tangent to the circle, wherever you were in the circle at that time. You wouldn't go, straight out. This thing isn't going to go this way if it breaks right here. It's moving this way at that instant. It would go. It's not going to go out like this. It would go out like this. This is the way the ride is moving you in. Like whatever motor is spinning it, it's spinning in. It's accelerating you in a straight line. The wall is what's pushing you in, and that's what you feel on those. Like in a washing machine, like you were saying, the drum of the washing machine. And I don't actually say wash, everybody. It's just fun to say wash, so I say it.
My grandma says wash.
Good. See, that's good.
I hope no one's rode a washing machine in here.
Well, sometimes you have to, or it's not. It'll get off balance. Anyway, where's Darian? We need Darian. Well, where was I? It was a washing machine. The drum is providing that centripetal force that pushes the clothes toward the center of the circle so they don't go flying out of that drum. Or if you're in a car, you guys ever been in a car? And you're going around a curve in the car,
And then you just,
and somebody is driving the car and they go around the curve like this. And you're like against the door or the window or whatever you got. And that door is providing a centripetal force that is keeping you moving in a curved path with the car. If the door and the seatbelt weren't there, then you would go in a line tangent to the circle like this. And the reason you would go in that tangent line is because of Newton's first law. Right, Jada? Object in motion, remain in motion with the same speed and in the same direction, unless acted upon by an unbalanced force, which in this case is the toward the center of the circle centripetal force. And that is what centripetal force is. It keeps objects moving in a curved path. The object applying the centripetal force here is the yarn. And it's not very good yarn, which is why it broke last time, but I'm not going to keep swinging it so I don't hit anybody. I want to do an example of one of the math problems for this one, if there are math problems. Here we go. All right. So, which one should I do? I'll do this last one, the 0.25s, I guess. So if you have a 0.25 kilogram ball, that's a mass. Kilogram ball on a 0.25 meter string. I guess before I plug that in, I ought to explain the formula a little bit. The formula is this: centripetal force. See, that's a F sub c. That's a C type of force, which is a centripetal type of force. Centripetal force is equal to mass times velocity squared divided by r. R is the radius of the circle. So this mass has a mass of 20 grams, which is 0.02 kilograms. So mass in this case will be 0.02 in my case of swinging this thing around. This thing, let's see, this thing is 30 centimeters long. This is the radius of the circle, because this thing moves all around the circle, right? So just the length of the string is only halfway across the circle, which makes it the radius. So if that's 30 centimeters long, my R would be what am I doing? 0.3 meters. And in this case, it'll be easier to calculate the centripetal force, like we did yesterday in the lab. Oh boy, I'm going to swing this one actually. Well, I can't because I just did that one.
Do you square the velocity?
Can I do it?
Mr. Brady?
Yeah, mv squared. You got to
Wait,
square the
so
velocity.
is the v squared or is it mv squared? So like
It's-
mass times
If it were
velocity
both of them
times-
squared, then it would be in parentheses. When there's not in parentheses like this, the only thing you square is the one that's on. So it's m times v
v
squared.
squared.
Yeah.
Okay.
So
That
velocity would be
makes a
36.
lot
Yeah,
of
so you
sense.
could square v first and then multiply that product by m.
Okay. Thank
Oh
you
man.
for clearing that.
So if I swing this super slow, I better use this other mass. Let's do it this way. This one's 10 grams. So in this case, my mass would be 0.01 kilograms. And if I swing it like we did in our lab, where it's not twisting around like it is, and it's not pulling this thing up nor letting it fall down, there we go. That's about balanced. I can calculate its velocity if let's see, I put the mass in. I know the force because if it's neither pulling this up nor letting it down, then the force is equal to this thing's weight, because this down force is being transferred into the string, where this weight is the same as the centripetal force that's keeping this thing moving around, and we can calculate its velocity. That's what y'all did in the lab, but let's finish doing this thing. So a 0.25 meter string, that's the radius. 0.25 meters. My marker didn't die even though I left it open. Moving at 6 meters per second. All right. So if I solve that, I got centripetal force equals mv squared over r. I'm looking for the force. I've got the mass, 0.25. I've got the velocity at 6 and a square. Don't forget your squareds here, that's important. And the r is 0.25. They ain't gonna run out of room and stuff. Anyway, I got a little bit of room still. 0.25 times 6 squared, will that be 0.25 times 36? And I know what 36 divided by 4 is. That's 9. 9 times 4 is 36, right? So 0.25 times 36 would be 9. And then I just got to do 9 divided by 4. Let's see, 0.25 times 36, that's 9. And 9 divided by 0.25, oh, I'm sorry, 9 divided by 0.25, it's not 9 divided by 4. But 9 divided by 1/4, that's the same as 9 times 4, so that's 36 again. And that kind of makes sense. Like we could have done it where 0.25 cancels with 0.25, and it's just 36. So it's a force, and it's in newtons. There you go. Please try out this practice. I got to start wearing those gloves again. Just a second.